I will not introduce again our panelists because we already done that this morning. Just let me give you a few highlights. So Davide is the driving force behind the Pulp project, hundreds of papers on that, many years of work in the open available community. And Mohammad has Best Paper Awards in DAC, DATE, and ICCAT. And David Atienza is joining us. I won't even mention all the awards that he has. Let's just say that his office can have a use for more space in order to, showcase all the certificates. So I'm very much humbled to be the worst researcher on this stage today, and I really mean that. Nonetheless, I do have some questions that I would like to ask to our panelists, but I hope I will not get through all of them. Instead, I hope that you will raise your hand and just ask whatever you're curious about to our three panelists. So, to start with, is there any burning question that you would like to ask as of now to break the ice? Okay, since that I have to do that. So, let's see. So, all of our speakers have spoke about having an holistic view of systems, hardware, software, and being able to address all the steps in this ladder. But in our work, we also like to have well-formed interfaces so that we can trust researchers in limiting fields to give us a good abstraction that we can work on. So in Edge AI, what is the state of building these abstractions and what you would like to have as a well-defined abstraction layer that at the moment you cannot really rely on?
So let me go a little bit deeper on that. So the first point is that there is a bit of a paradox here, which is when you want to optimize, you really don't want to have the abstraction levels. So that's a bit of the issue that we have here. So HAI, and you see the examples that actually Davide has shown, when you really want to go to the really nanowatt that you're actually saving here and there, it's very difficult to create abstractions. Now, having said that, I think one of the nice angles that we have in HAI is that it shouldn't be like hardware or software, but it should be a definition layer, which I'm still thinking about how to do it, but I think we have some hints on that, where you define basically what you want to have as functionality, and you define later on what you build it. If it should be hardware or software or how to do it. Now, it's true that traditionally the problem that we have today is that you have people building machine learning, which is the machine learning community that came from there, and also people that build systems and hardware, we came from here. So now it's very difficult to get there, but conceptually, I don't think we should think of how to segregate or divide in layers. We should think of a language that describes, or a way to actually describe a functionality. And then we should find ways or methodology to create metrics about, okay, how much will it cost in hardware and software and how to build it. Now, we have heard a lot about UML languages being recreated now, high-level description languages, HLS, and so on. I think we are still missing the problem of what is the actual final architecture for machine learning you want to use. I don't think machine learning solves everything, but I think we go from these abstraction levels and we retake them. UML and so on have very nice properties that we actually never used. So that's a bit of the thing that I have. So I think we should go in that direction. Functional description languages.
Functional description. I think it's a interesting question, because in my presentation I was saying that cross-layer optimization and layers should be talking. That means I didn't want to advocate for any separation or any separation of concern. But we already learned from earlier system design that you have to have interface. Am I right? Otherwise scalability cannot be maintained and cannot be basically building harder, difficult, complex systems. We cannot build it. So I think are we there? Of course not. I think we are all still talking about co-design into trying to bridge, optimize it as much as possible into the edge AI. But in a general purpose AI, people are they are in a larger system. They can probably use the interface. They have come up with lots of tools. lots of different architectures to start with. But for Edge AI, I think it's a harder problem. So I really believe that we are not there yet. We are not there yet, but at some point, some modular approach, that functional language that David was mentioning, might be a good starting point. And then from there, probably we'll be able to separate the design process. But at this point, I don't think, even the architecture, that instruction set architecture that we are talking about, moving from different hardware platform to different hardware platform. I think the point is we need a lot of tools. I personally believe that there will be a lot of tools coming to bridge this gap. And as more and more tools will be able to build to do this thing, at some point we'll be able to separate these things. And multiple vendors or multiple stakeholders will be able to work seamlessly through those tool chain. That's probably I'll be
Okay, so I also think we are not still there yet. But so in my view, there are two different points. There is one point which is related, let's say, to the design of energy efficient computers for AI and also algorithms. And the point here is related to how to evaluate the correctness of the models which are used by, let's say, computer scientists or the higher level to develop algorithms. So what I have seen in many work in the research is that these models, let's say, are not accurate enough to deal with the real underlying hardware, and not having enough accurate models. Basically, you are not able to optimize the algorithm to do whatever you want, or to achieve the desired level of energy efficiency or performance and so on. And this is, let's say, one aspect in this field where, let's say, the interfaces between the different levels of abstractions are more well defined, because people are working on this since decades. And the other aspects I'm less aware of, but I see even more challenging, is how to move to the next step, to the step forward. So optimizing systems where there are computers interacting with electrical components, interacting with mechanical components, like the examples of the autonomous driving for automotive. Let's say I'm not an expert on this, but I think that this will be the next challenge, how to put together systems which are extremely complex, heterogeneous, and does not only involve computers, but also other components.
So I broke the ice. Yeah, we have one hand up.
All three of you have talked about finding a unified or holistic language for designing cyber-physical systems or hardware software systems. Have you heard of the Circuit project, which is based on the LLVM compiler framework, which is, I think, trying to do that with different levels of abstractions on different intermediate representations? And as a second question, especially what Davide said about the cyber-physical systems, isn't cis.epfl such a language that could leverage the gap between software and hardware, and mechanical hardware?
So very good point. So let me start with the second one. So the second one is cis.epfl, which is actually exactly so a little bit going in the direction I was saying. So I was talking about all types of functional languages like UML, cis.epfl, all these. They go in the right direction in the sense of describing the thing, but actually, in my view, they fail to actually cover the heterogeneity of the underlying hardware that are behind, which is basically what Davide was talking about. You really want to go from this high-level description languages, which is actually pretty intuitive somehow. We can make it even better, but pretty intuitive from a functional perspective to describe the functionality of the system that you want to build. How do you go from there to the part of the cross-layer optimizations that Faruque was talking about, without losing, saying, okay, I only work with one system because it's the only one that I know very well how to do. When you have 300 different types of final platforms, how do you actually cover all of them without all these steps? I think this is one part. So that's why I'm saying that I think we should go in that direction, but I think there's a lot of interesting area that should be in the middle level, how to go a little bit deeper and actually reflect, propagate the dependencies of the lower hardware for this functional level. But I think it's a good starting point. I will definitely go from there rather than taking BASDL and making it richer, because I will not go anywhere. Now, going back to all the LLVM initiatives, and then you mentioned circuits, but it's one, but there are many others. I think that's the problem, which I was referring. I think they are going in the wrong direction. They start from lower level aspects and trying to go a little bit higher up, but this is very far from what actual users want to take to define the problems. So you think about any data scientists that actually are defining their problems today, or you talk to a doctor, how they actually will look at the problem, to explaining how LLVM goes and the abstraction level they need, it will take you longer than if you write it by yourself. So essentially, I think that's the main problem I have with all these options. So I think we are starting, we know that this is the efficiency and we go from there up, but I think we have too many layers up. I think it's easier to go the other way around. Because in the end, even without going for the extremely high computing HAI, as Davide showed, we have plenty of computing power. The problem is to use it efficiently. Well, if you really want to squeeze the last final nanowatt, fine, then you spend more time. But if you want to really put a mapping from the high-level perspective to something that works more or less, you can afford to spend a few more watts, but they're saving a couple of years of description. I think that's my angle. Any other?
I think you answered it, I think.
Any other question, guys, on this?
Questions? Okay, let me try. Oh, go ahead.
At the bottom of the headset, there's a red button.
Can everyone tell me?
Yeah, we can hear you.
It's for recording. Hello? We have seen. Okay, I can try again. Hello? Perfect. Okay, so we have seen many different perspectives today, like trying to tackle multi-sensor prediction on a very low-level architecture approach with the RISC-V and ISA, like creation of new instructions and the pulp architecture, and with different like very specific instructions. But then we go to the application side, where you have medical applications where you have to merge different information from sensors to predict something or make a decision patient-wise, which is very, very specific. This is very interesting. But then you have something it's similar, but not so similar for autonomous navigation. Again, you have multiple sensors that have to be merged together in order to make a decision for navigation, for detection, for tracking, for prediction. And all these levels of attacking the problem of combining information from sensors and making decisions, I see like the need to be an expert in so many low-level things in order to be able to assemble a holistic solution. And it's very hard, it's mind-boggling. Is there any work in progress to try to make portable solutions and more productive ways of integrating these solutions that are very similar for like medical systems and autonomous navigation systems? Some are ultra low power, the others are just low power. Is there any work in progress to try to make like an architect's life easier to integrate what's out there? Because David was saying, okay, if we want the very, very efficient systems to get rid of the abstraction layers. But if you do that, you cannot port those solutions to like a new problem. So I mean, it's good, but it's complicating our life quite a lot to reuse what we have.
I can talk about it here. Okay, I can start. I think probably I understood the question. So let me try to understand. I think it's a larger question that you asked. So if you follow how things have been changed since 2006, we all know the term cyber physical systems, and I had been extremely excited about. I was still a graduate student at that time, and when I graduated, started working on that, and started becoming really a good member and part of the cyber physical system. So the challenge is in 2006 that there was a reason that in NSF or the US government was pushing for this type of new type of education system, not only a research agenda, because now you see that there is a new degree program, Masters in Cyber Physical Systems. Or many places they are starting undergraduate in cyber physical system. Because the thing that you are talking about, that hardware software co-design, designing system at that level, the complexity was already huge. And we had been trying to tackle it. Then we brought physics. We quickly understood that it's a medical sector, it's the automotive sector. If I don't talk to doctors, I know Davide was mentioning that he has an appointment with the medical school. I have an appointment with medical school, law school, mechanical engineering. I think the world is changing a little bit. So the problem is that I can afford, probably as a professor, David can afford, but the question is that as an engineer, how do I afford basically this type of thing? Where is the abstraction coming? So these are fundamental questions. And as an academic myself, and I ask the same question myself, that what do I teach my students? How do I make them expert? I think the first thing that I can tell you, the interest. I think the current graduates or the students needs to be interested to learn and start talking to the people coming from other discipline, the application people. So the way you want to say maybe here, that automotive engineers or the medical people. And if that interest exists, I think the understanding the physical dynamics and the understanding the application, you already took the first step. And then once you can understand, and then the hardware software, the thing that we are expert in, I think can be tackled together with the physical part. And that was the purpose of bringing cyber physical systems. So larger initiative has been taken. And in this, if you follow the cyber physical systems community, you will see it's pretty much embedded system plus, control plus, formal method plus. Everybody came to this community and tried to work together. There has been a lot of tools came up that people can talk to each other. I think the conversation was the problem, that how to start the conversation. And once you can start the conversation, then you'll see that either it's a machine learning model or a low-power design, or you're talking about improving some of the things can be considered. And you will see that many similarities exist. And now as an expert, like academics, you will find similarities. And also there are the differences that you will find can be handled through conversation. So you don't need to be expert on everything. But the point I'm trying to make here, that you have to be ready to talk, and you have to know the semantics, or maybe not only entire semantics, or syntax, to talk to a people who knows the biology. Talk to a person who knows the automotive. And that's where I want to end, and maybe I want to ask others if David or...
No, I think I completely agree.
Okay, so I gave my point. Maybe David can add something.
Yes, so maybe yes.
To understand my point. Yeah.
I think, I fully agree with the part of talking to multiple levels. So my only statement, there are two. I think one is more controversial and the other one is more reasonable. I think the more reasonable one is clearly that the complexity is there. Now, my argument is that the more and more you think about the ways that you tackle different areas and different fields, we basically rely on the basic fundamentals of, and I'm going to simplify here, maths, physics, and problems and modeling. So now, the problem of why you take an issue with modeling epileptic seizures, you had no idea. Well, because people were looking at this in a different angle. You look at it, you bring another perspective, and they suddenly, the same type of methodology or multi-agents that we're using for monitoring data centers or servers work actually here. Now, the point is that nobody will use them until you understand the problem. It goes back to the problem of what Faruque said. So you don't understand the problem, it's difficult to do something. Now, what I was going to say, I think this is pretty reasonable and we are going in that direction. Many more education programs actually go in that way to show you multiple dimensions, you can talk to more people, and we even create languages that you can actually understand each other, more or less. Now, the more controversial one is like what I'm going to go now, is that I think we have an issue with machine learning. With machine learning, people had the concept that, you know what, I had no idea about the problem, but I just take a model, I feed in the data, and they will solve for me the problem. Essentially, I mean, if it was true, what I would actually say is like, I don't want to spend the effort of understanding the problem, but let me give the effort to this machine that will just take the data and figure out what is actually coming from the data inside. And I think this is wrong, absolutely wrong. And actually, you know, by principle already in the lab, every time that somebody uses a machine learning algorithm and can say, okay, this gives me great results. And I think goes back to the concept of interpretability of machine learning. That's where we should go. Can you explain me what the heck the machine is understanding? I had no idea. I'm sorry we're not publishing this. When you tell me what the machine is understanding, then we can think about actually publishing this more reasonable. But it doesn't make sense. And I think so far, so good. We are more intelligent than machines. I hope we keep remaining that way. The machine learning should help us. We shouldn't replace it. And I think this idea of trying not to do the effort of talking to someone else, saying, okay, you take a model from image processing, I take transformers, I put them here, they will solve the problem, I think is wrong. Fundamentally wrong. And it's my observation. I think the people from machine learning will not agree, but this is my observation about the problem.
I think it's the right point. If I can add with you, I was the graduate advisor in the last several years. Every application, thousands of applications I was reading, everybody wants to do machine learning. Why and how? No idea. But I think that's a fundamental problem I can add with David, that it needs to be, I think challenges are same. You need to understand, go back to the problem, hardware, software, physics, math, and then you ask yourself, do I use machine learning? And it's just a tool, another tool, am I right? And we are trying to use that tool appropriately, and I cannot agree more with you, yeah.
So let me follow up on something that Mohammad mentioned, which was about being able to talk with each other. So even from the speakers of yesterday, I understand that software guys, they would like to do more and more with bigger and bigger models. Hardware, software, edge AI guys, we would like to do less and less to be as efficient as possible. So do you think that we are reaching an understanding little by little, or we are just drifting away further?
If you want to answer?
I will answer that.
Okay. So, no, I think this is wonderful. I think it's an advantage that the theory people are doing a lot more interesting work, and I have no problem. Let them do that. And we as an embedded systems or systems people, there are two types of systems people also at the same time. Community systems is a very big buzzword by itself. But embedded systems engineers are, I think, we started and we are observing and looking into these different theoretical stuffs coming, and we really care about few things. Deployed system. We care about the form factor. We care about the energy. We care about the power. We care about privacy. Can we really build a thing? And I think there is no problem. I think we are. Can we converge and respect each other? And I think that's the problem. Am I right? I think that's the theory people, not all of them have good understanding about the challenges that coming from the deployed system or the hardware side or really building the system. And I think it's fine. I think it's fine. And I think this is our problem. We are tackling it nicely. Yeah, we're trying to do that. Yeah.
I also think that let's say this is one of the fields where there has been more advances very rapidly, because there is, let's say, a very well-defined and standardized interface between the network models and the hardware. Okay, which is basically ONNX, which is used to as interface between the training tools such as PyTorch and the deployment tools. So having this very clear interface and very well standardized, because this has become basically a standard for everybody, allows, let's say, a more tight interaction between the higher level of the research, where people are trying to develop a new model, even if they are larger, and the lower layers where people are trying to deploy these models in a very optimized way to the hardware.
maybe I want to cover the part of that was mentioned less, the part of can we converge? So I'm a little bit more optimistic than Faruque. So he said, no, we will not, anyway, we don't need it, which is actually, I think is a good angle because we have good things to do on our side enough for that. But I think we are going to converge. And actually there's an interesting movement in the machine learning community, the deep learning community. And I didn't see too much yesterday, but for example, people in Meta, people in Google have actually been looking into that. The idea of, well, these huge homologous models where we keep improving the models in the sense of adding 20 more layers and getting at 1% extra increase of accuracy, it doesn't make any sense. I'm sorry. You think about from sustainability perspective, and we hope we can get there, all there, agreeing at a certain moment in time how we build models and how we make a world sustainable. If you make a neural network of 200 layers to actually understand how to rule a traffic light, I'm sorry, there's something wrong. We have been doing traffic light for many years. The fact that you actually have to do it because you don't understand the problem is not a good idea. So I think there is a whole trend now, and actually you have few people in the medical imaging community that are going in that direction that show that even these very deep learning models can make mistakes. And one very good example that was presented a few years back in the EcoCloud annual event, and I wanted to mention that because I think we started discussing with them and they are very interested on these optimization problems, is that you take a deep neural network that is very well trained for something, for some types of tumors. You pass it through, it's conceptually perfect for some types of tumors. And you pass another type of tumor and actually misses completely the tumor, then there's something wrong with it. And if we actually suddenly take the same model, but we make the layers that actually what David was saying, that indeed they are very well understood how to map because they are simple, dot product actually operators, convolutions that are very well understood. You map them in hardware more or less efficiently these days, but they have issues on understanding the conceptual problem they want to solve and finding really the roots of the problems of the tumors. And they replace that by more complicated layers. And they were showing splines. I have seen other types of different complex systems that they put as basic operators, and they work much better. And then suddenly the network is reduced from these 150 layers to 20 layers. I think that we have a convergence. So point is that at the system level, we can definitely make accelerators much better than the pure GPUs and so on. We can make them work very well with the splines and some other complex operators on the individual level, because we've been doing that for embedded systems for many years. And then get rid of these 200 layers, make them maybe with 20 layers, 15 layers. And I'm hoping that we can converge there. Now, this is not massively shared by the machine learning community, but I'm hoping that few more results that showing that deep learning is a good starting point, but I think it's not where we are going to be there. I think hopefully we can get a convergence between both, which does not prevent that we do efficient hardware like what Mohammad and Davide are doing, but I think we can actually try to converge together.
Are there any questions from the audience, curiosities? Yes, please. It's just for the sake of recording.
Just one score, like how does that work? Where do we this one?
Should work now.
Ella?
Okay.
Yeah.
But yeah, okay, it works. I have a more general question. Yesterday we had a lecture on pruning, and we showed that models nowadays keeps getting larger and larger, more and more complex. I'm not very sure if we'll be able to actually decrease their size with the current techniques we have, or maybe at best we'll keep them constant or something like this. That's the first trend that I see. The second one is hardware related. Like when you talked about NVIDIA and the material they deliver, it seems that the way they tackle the computation for more and more complex is just by producing machines like tools, electronics, I mean, that consume more and more power. So with respect to Edge AI and the Internet of Things and this growing industry, how do you see the use of power and maybe the critics that may come with respect to how much power actually this industry, our industry, also machine learning, consumes and will consume?
But actually, this one is a little bit related to what I just answered partially. So I think the model should not be going bigger. And interestingly, there's a very nice paper from David Patterson, actually, from Google, explaining, just probably some month back, explaining that how machine learning and deep learning trends of energy consumption are going to flatten. And he claims, or he argues, he advocates it's going to go down. And he talks about a bunch of factors that actually will go there. One that he claims, and I said we have some examples, not really massively followed by the machine learning community because it's simpler to actually make more complicated models, but there are some trends that show that you don't need to make very complicated models. You need to enrich the simple level features that you actually have there with operators that are more complex than convolutional networks to actually make them really dramatically smaller in the number of parameters and features and sizes that you need to create solve a problem. So this is one of the trends. On the other trend, what he was talking about is indeed what we can do as a systems community in reality. So one was, of course, a specialization to make really specialized hardware. You cannot use NVIDIA GPUs all the time. Unfortunately, it doesn't work like that. It's actually the energy consumption they have is dramatically worse than what you will have. You take custom accelerators, you're simply dumping them on FPGAs. So you need to have more co-design, but I agree with Faruque. We have enough tools to make the system work. You automatically will do that much better. And actually, that's one of the reasons why AMD and Intel have actually bought both Altera and Xilinx to try to compete a little bit with what NVIDIA is doing. And finally, from the point of view of how you operate, I think there is an issue on the cyber-physical concept on how data centers and all these machines work. Because you put something to run there, you expect to have the answer in 2 minutes, 1 minute, 5 minutes, or if it's too big, hours. But when do you really need the answer? That's the main point. So why don't you actually run the system at a much lower pace when you have availability of renewable energy or something, and you make it run when it actually makes sense, in the sense to really make it much more sustainable. So I think there's going to be a part of regulating how you use the energy, because it will be impossible to keep the current trend, and also really hardware specialization. And I hope this trend of machine learning simplifying models will actually go further, not actually go worse. Because if it goes worse, we are not going to go anywhere. I don't think we need machine learning for anything. We just need to find a way to actually save the planet. That's how we're going to be. But,
I think it's a wonderful question, to be honest. Most of us had been talking about micro-level energy optimization. I think if I understand correctly, you had been talking about global scale and really the large green energy. And I think David has answered already the trend into this thing. But you cannot stop really, because we are talking about 75 billion of these devices and maybe more even going forward. So I think we have to be realistic that what NVIDIA is doing, definitely there is a need. People are asking, and that's why they are increasing their computation power at the same time sacrificing and building much more energy hungry GPUs and putting them on the car. And that's why I gave you number. Almost 12 to 13% power, battery is consumed by your computing these days, which was unheard of just few years ago. Even a traditional car, not more than 1% or less than 1% is consumed from the battery for computation. So the point is here, I think again going back, that what we are doing here in this room, what we had been talking, that micro-level energy optimization, as much as possible, to the last bit, what David was trying to do using his pulp architecture. We have to continue doing that. At the macro level, what David said, that renewable sources, energy management at that level, I think so these two things will continue growing, and more and more, I think that's the trend. I don't. Am I happy? Of course not. I think none of us are happy, because no matter what we are talking, we are consuming more power. No matter what, every year, every day, our total power consumption globally is increasing. Am I right? So I think we need to definitely come up with a different strategy. But again, we need to do our job that we are doing in macro scale and macro scale.
Yeah, I just wanted to add that I think that the problem of consuming more and more power is not only on the edge side of the Internet of Things, but also on the training of the machine learning models. So this is also burning quite, let's say, huge amount of power and huge amount of energy, and I think this is going to be a problem. So I think we should go for more optimized and specialized architectures, not only on edge devices, but also on HPC systems, large HPC systems.
So let me follow up on the hardware specialization aspects, which is something that all three of you have covered to some degree. So we are seeing from Davide examples of how you can do hardware specialization for Edge AI, but there's a lot of solution out there going from multi-cores, many cores, specialized memory hierarchies, in-memory computing, RAM crossbars, and many other solutions. So do you see trends emerging? Do we have a clear winner yet? Or the jury is still out on what is the most efficient path toward implementing specialized hardware for Edge AI?
Okay, so let me just go. So I think we have a very simple answer, which is, I think, thanks to Davide, we know, which is there's not a single pulp, so there's not a single solution. So if we have one solution, he will have already tried to find it by now, I hope. So that the main point is that I think it's really application dependent. So now that you have large models, small models, many different things. And I think that's also one of the beauties that we have in this domain, and I hope we have it more and more. And goes back to the question of the cis.epfl and this type of things. I don't think there's one model fits all, and actually that goes back to the hardware. So I don't think there's one solution that we can actually have for every single problem or things out there. We are trying to simplify the idea of using machine learning for everything and one simple type of model, but even the models are not unique. We have plenty of different models and so on. So I don't think there is a single solution. Now, from a disruptive perspective, I think we are going to see more and more, if we go in the direction of having simple models and broader, we are going to be seeing more and more the completely disappearing CPUs. The concept of CPUs, for me, is actually the thing that more and more don't make any sense. Because if you think about, if we want to be a little bit disruptive on that, we see that it's all machine learning and this type of things. And if you go in that direction, 90% of the power consumption of many of the models are because of the machine learning, and the control and the CPU is not doing much. So why do we need multi-core CPU and so on? Why don't we have a bunch of accelerators that if we have a good unified model to dump all these things into customized blocks, we have them all there? That would be, I think, what would be the trend. And then particularly for models, I would say, I think there are two trends. One is do the near memory computing, and the other one is the in-memory computing. And my bet will be that if we really see the idea of having even more complicated modules with more data and so on, but simple operations, I think in-memory computing can help quite a bit. So if I'm going that direction, the energy that goes for near memory, I think is not going to be very often compensated. So you manage to do this in-sensing in computing on the sensor and so on, in-sensing computing. I think you will have more and more type of in-memory computing as a very big winner, and the CPU trend going out. So that's what I would think. Yes?
So David, analog in memory or digital in memory?
That is a bit tricky. I don't like too much analog, to be honest, because they're not very precise. So that I think analog makes sense. The current trends I have seen, I think, makes total sense for inference, because very often you don't need 100% accuracy, and very often it's very much easy to process. But I think training still is much easier to do it in digital, at least with the current abstractions. But
I will leave it for Davide.
Yeah. Okay. Yeah. So I think that so the problem here is clearly still open, and the main problem we need to find out and to solve is to find let's say the correct trade-off between specialization and flexibility, because so if you talk to software guys. They want to deploy different models. They want to be able to change everything, and as David was saying, to find other kind of operators beyond convolutions. And this, let's say, from the specialization perspective, would be a pity, because I mean we all agreed that convolution and matrix multiplication is a good, let's say, is a good kernel for everything, and we developed a lot of heavily specialized architectures such as Google TPU and so on, which are very good and efficient in doing this. But on the other hand, let's say the application guys wanted to have more flexibility. And so I think that what we need to understand is this aspect. And about in-memory computing, and in particular analog in-memory computing, I think it's a, let's say, promising technology. But in order to fully exploit this technology, let's say we would need software guys to think about the architecture, because we made some experiments with analog in-memory computing blocks, and what we have seen is that if you deploy current models, let's say, to this block in an end-to-end application, these blocks are not flexible enough to deal with the complexity of the models, and maybe you can achieve tops per watt on a single convolutional kernel, but then when you go and you deploy all the model or all the application, you hit the Amdahl law, and in the end you gain the gain in energy efficiency and performance you get from this kind of accelerators is not so high.
So yeah, we are in a nice pattern in which I ask a question and then the audience asks a question and we alternate. So I really appreciate that. Please go ahead.
When talking about specialized hardware, we only talked about CMOS. Could you give maybe a perspective of post-CMOS architectures on the edge, if you can?
Yes, so to be fair, I didn't really specifically talk about CMOS. It's true that accelerators today, many of them are built on CMOS, but you think about, for example, memory technologies, any of the resistive RAMs, anything like that, yes, you can think of it of CMOS. But if you think of spin-torqued transistors, how to actually organize some of those, they provide many other opportunities. I don't want to go into quantum, for example. On the other hand, when we talk about post-CMOS, very often people include quantum. I don't think quantum is the same ballpark. It's completely different angle. Very narrow spectrum where it actually fits. But I think what we have to do with all these new CMOS technologies is to think, or post-CMOS technologies, sorry, is to think about two key points they have. One is, most of them, they don't have the level of resilience that you have on CMOS. So very often they have either resistive RAMs or anything like that. They will actually have a huge degradation when you do a large number of reads, for example. And it automatically limits a little bit the operation of this type of technologies for current architectures. And I think goes back a little bit what Davide has been saying. You have to think how to map these algorithms to exploit the features of these new post-CMOS architectures or technologies. If you think about that way, then you will be able to really exploit them very efficiently. We have seen some of the worlds doing that, but still, I think there is a challenge here because the main vendors that they still produce CMOS-based systems, they still manage to get extremely high levels of efficiency with respect to what we actually can achieve with the other ones. So it's a bit of a chicken and egg problem. You need to develop the post-CMOS technologies to be able to reach something competitive with the others. And that will imply that the designers of the apps think about these features and make them really work well, better than the CMOS. Now we have examples on papers that, yes, you can get 100 times, or tomorrow you will have some examples coming from Professor Subhasis Mitra where they claim 1,000 times more energy efficiency. You build different types of integration with CNTs and some other things, but it's just one chip, unfortunately. And actually, it's one chip custom built by the team of 20 people and actually costing one single sensor $100,000, which is actually a bit tricky to sell to typically customers. So, but I think there is a lot of potential. Now the problem is on the maturity of these technologies and the designers that can use it. I think that will be a bit tricky to do for the moment. Maybe wait until they get struggling in 3 or 2 nanometer technology, and then we will see more actually coming from the big vendors. So it'll be like carbon, solid fuel, and actually renewables. So when you think about that, then there will be a problem that will start.
Yeah, I think you answered already. Any post-CMOS technology has the problem, am I right? So we had been at least hearing it for at least many years already. They're definitely promising. Many of these things, I'm sure, as Shubhashish is present, as David was saying, CNT is one possible option that is really promising. But I believe CMOS is here to stay for longer. You can't really ignore CMOS. Many more years to go. And we are going to 2 nanometer quickly, and then we are building architectures, 3D, and different other organizations who are going there. So it will stay there, and slowly, possibly just different memory technologies will get integrated. So any solution, commercial solution or viable solution, I think we have to rely on CMOS still going forward. That's my take. But I'm not saying that we'll not do research and continue investing on post-CMOS technology. We have to, and we are doing, and we should probably even expedite that process and make it happen more. But I think both will coexist. Maybe in that case, after a few years, both will coexist for many years to go.
Yeah, I mean, I also think that CMOS will stay for a longer time. Yeah, I think that maybe some, let's say, there might be some geopolitical, let's say, aspects that maybe might improve some parts of the world to push some part of the world to work toward different technologies.
This can be a driving force, yeah.
So now we have to interrupt the pattern because there is one question from up there.
Hello. Can I ask 2 questions?
If they are short, yeah.
Okay. The first one is how do you see the relation between the relation or correlation between the explainable AI topic, which deals with the simplicity and complexity of the deep neural networks, and the edge AI? And then second question is the question which I asked also yesterday, which I want to ask you as a researcher and scientist in the AI. How do you see the future of the edge AI, which between the data, algorithm, and hardware, which of them would be more important in the future or would affect the field more than the other ones? And that's it. Thank you.
Okay, so anybody wants to ask one or both?
I can answer the first question probably. Sure. So very interesting question. In fact, I did not present. One of the things that I could not finish, the split architecture, dynamic architecture, if you see. I splitted the network, just an example, rather than giving you the other answer. Before and after the splitting, how do I verify the model? Before basically splitting and after, if the specification that I started with, and then I split it using my controller. And for example, we have seen that in autonomous vehicle, if we split the architecture, the latency changes. And especially motion prediction and other application, before the behavior and after the behavior, splitting is not the same. So you need some sort of runtime verification or design time verification tools. And in fact, these are the hard problems. In fact, we're still not there. In fact, I'm happy that you asked this question about that. Even when we are doing quantization, too much of quantization. We started with specification using SysML and all other high-level specification language we started with, and then started doing a lot more optimization. And once we have the deployed system, the specification and the deployed system might not basically conform each other. And at runtime also we are taking decisions. So this is, I think, probably was not your question. Explainable AI is something different, I understand. But this is one aspect that needs to be considered. But explainable AI that you are also asking, that your decision making, we need to understand why that is happening. Especially in US, like there was a large DARPA project. In fact, last several years, it's still going on. That autonomous vehicle, why these decisions are taken, where in the intermediate levels, basically layers, these features were changed, and what is the trace back? How do you trace back to the data? And this is probably one of the most important research challenge, which we did not talk at all. And I don't know whether there is any speaker tomorrow. I don't believe so. But this is a different aspect that you need to be concerned about for any safety critical system. Any autonomous systems, any medical systems, explainable AI plus formal method and verification is important, and they are harder problems. And I will skip the second question, so if anyone wants to add in the first question.
Yeah, so for the second question you mentioned, what do you see more in the future, actually? That's a bit of a tricky thing, because regarding is more on you said on the algorithms or on the systems?
Yes, between the algorithm, hardware and data, and also are we going to decentralization similar to the other recently hot trends such as the cryptography or some cryptocurrency and something like that? Are we going to decentralization in the AI or not?
So I think that's why I wanted to check if I understood correctly. So my strong belief is yes. So clearly there are many arguments we want to decentralize the whole process. So first of all, of AI, there was an interesting lecture on federated learning and so on yesterday, but I think fully decentralized models have one part which is negative, which is of course the limitations of the observability of what you have on the data to train your model. But they have a beauty, which is actually some that goes in the direction of what we have said here about privacy, preservation, and constraints that you have in multiple parts. So you have to actually train a model where you have to get all the data coming. Let's say you have to train a model about prediction of financing or investment, and you have to bring all the data coming from the US to China to Europe and put it together. I don't think the banks will be happy with that, just to make it clear. And then the point is that for sure you need to find ways to actually create interfaces on between different AI models that actually work in a distributed way. And I think that's the only way to solve, not from the point of view of federated or privacy or something, but also from the point of view of sustainability. The effort of migrating the data, moving it from one part of the world to the other side of the world to just train it, move aside all the costs that actually Davide mentioned about training algorithms. So say, we train it here, but we want to train with this other model. Okay, bring me all the data to train it. It's completely unacceptable. You cannot really work like that. So I think there was a moment where we wanted to find the limits of what would be actually centralized models and so on. I think we are reaching the point that actually with the current schemes that are there, you get to see what they are. Now you want to try to create something like that, but actually in a distributed fashion. And that's where HAI works very well. And I think has a lot of things to say. Because you want to really make sure that you train the data as much as possible local to where you acquire the data. And if there is something that is relevant for the models that actually are there, then you send it. And I think also in the direction of what, in this case, Faruque mentioned, when you have the models that you split it, you had the head, the tail, and so on. Well, some parts you train it, some parts you don't need to train. As long as you know how much you're losing of precision, if you do it in this way, I think it's the right way to go to actually make sure you make sustainable this trend of AI.
Thank you.
Please go ahead.
I would like just to take a slightly different angle. So I think that I answered the question between hardware and data. Which one is more important? So I think that the success of let's say artificial intelligence was given by the availability of data, because there were these huge data sets for training of neural networks, and also of hardware, because the GPUs basically become powerful enough to be able to train the new model and demonstrate that with these models you could do something, and this happened more or less 10 years ago. So if now we start from this concept and we want to bring this concept to the edge, I think that we will need still both data and hardware, because now we have a lot of data, because we have a lot of sensors that can gather data from everywhere, but I don't think that we have yet, let's say, the proper hardware deployed at the edge to demonstrate what we want to do. For example, part of the training done on the data centers, and some refined training on the edge, and so on. So I think that I think that we have the data, but not yet the hardware to be deployed.
Further questions from the audience? Okay, the right wing is very silent, so yeah, if any... okay, got it. So, okay. Yeah. So, oh.
We good. Sorry.
We have time for both, don't worry.
Just because you wanted a question from this half of the room. Yesterday there was talk about, sparse networks and stuff. What kind of directions are being taken for implementation of sparse networks? It's really a question to you, David.
So the question was about sparse networks, yes.
Let's say it's a very difficult topic because on one end, by exploiting sparsity, you can reduce, let's say, a lot of memory occupation and so on. And on the other end, you break, let's say, the regularity of the memory accesses, especially. Which are, let's say, one of the key advantages of what I was showing in the presentation on tiling. So I think that actually in our group we are doing some work with respect to this problem, but more on the, let's say, high performance side of the spectrum, where, let's say, the amount of data you need to process is much larger. And I think that also with respect to this topic, what we need to do is to find the correct trade-off between, again, the flexibility and specialization. And in this case, this is not related to the, let's say, key computing elements of the network, but is related more to the memory accesses. So we need to build a more complex structure that can be used to access data structure in memory.
Yes, please.
Yes, this question is for you, Professor Faruque. It's about your XNAS architecture for searching via multi-objective Bayesian optimization. Could you give us a feedback on it and how well it worked, its limitations?
Multi-objective optimization?
Yes, for the early exit NAS that you talked about earlier.
So one of the drawback that I already mentioned about that, if you want to build any dynamic architecture, you basically sacrifice, your network is quite big then compared to the fixed architecture, am I right? And you gain in the energy side. And also you need a controller, so that comes as overhead. So these two part, I would say that how big is your controller, that's you have to account for. If you want to do any early exit or split or even the sensor fusion that I was mentioning, because all of them depends on your performance of the controller. So this is the overhead, I would say. So if you don't build a better controller, your results can go basically bad. And that's the parameter you need to concern about. So in the design of NAS network that you had been showing, when we use the Bayesian optimization, in the Bayesian optimization, there are other techniques also for NAS that people have shown. In the Bayesian optimization, if you can choose the optimization criteria rightly and can try to find basically the right architecture at design time, and at the same time can come up with a control algorithm that we had been designing mostly coming from the physics side in this case, I would say, for the application, for the healthcare application, that both on the signals that you had been looking, then you probably will gain much better results. So optimization, you need to be concerned about how you specify the loss function and basically the objectives that you are talking about. Yeah.
So let me interject and let me try to be a little bit controversial here. So when I started to be a researcher, there were all kinds of computational kernels, and actually discovering computational kernels was an active topic of research. So right now it seems that we have dot products and variations thereof, matrix vector, matrix matrix, but basically these are dot products. So is this all that there is left for us architects, the optimization of dot products, or are we missing something here?
Do you want to start?
Maybe.
Yeah, okay. Yeah, I mean, I think that maybe 95% of the research community moved to AI because, I mean, it's more convenient to deal with this kind of applications. But I think that, I mean, in the real application, the percentage of applications and the products using more traditional algorithms is reverted. 95%. Maybe traditional algorithms, PCA, FFT, I don't know. All, let's say, the old crocodiles never dies.
Yeah, I think he answered already. You know, the reality versus research push are very different at this point. So, but again, I think that's the nature of the research these days. It's hard to control your dot products research and all these things, machine learning. Because it's driven by manufacturers, am I right? It's driven by students, industry, government, competitions around the world, and so on. So, but the reality is, as David said, that still the old algorithms are in real deployment most of the time.
I was going to actually make something a little bit similar to what Faruque said. So it's not only a problem that is the only one. No, it's not the only one, but it's what you get funding for. So that's a bit of the issue. So it's what you get easily the funding, and you can actually make a new proposal, optimize NFFT, and they will tell you, well, this is old-fashioned. Why don't you optimize transformers? I said, so it's a bit tricky. Now, I fully believe that this is not, and I mentioned that before, goes back to the part of which type of systems we want to build in the future. I think dot products are not going to be the only ones. Actually, they don't solve all the problems that you have there. And matrix multiplications, unfortunately, or fortunately for us, this is not the only problem. So otherwise, I think we'll get bored before we graduate, have all the students. The idea that you think about full applications, and we are looking at, not from the point of view of just applying machine learning, but you really look at the application, you understand the signals. For example, if I go to the medical domain, filters, FFT, and so on, they are still the most prominent way of doing this. I mean, yes, you can take a dumb neural network with 25 layers, we do something similar. But in reality, you think about what it's doing non-linear interpolations and things that actually you can do it in a much simpler way. So I think I don't have you as a graduate student, but I will be very happy you look for kernels that actually are different than dotted products.
Any more questions? So, okay. I don't know how much time do we still have, because I would have a couple more questions which may be interesting. Okay. So, one question is specifically for Davide, so I'm sorry for the other panelists, but you briefly touched on the topic of open hardware during your talk, I guess for the lack of time. Can you briefly explain what is the state of the art of open hardware for Edge AI specifically, and what is the value proposition there? So if everything is free, how can we build an industry out of that? Or is there a role for profits in an open hardware scenario?
Yeah. Okay. So my view and let's say what I have seen so far is that open hardware is going to be used by many companies. But for all the components of the system, which are let's say the key element of the system. For example, for a company doing audio processing, okay, you need a very powerful specialized accelerator or ISA extension to do your algorithms, and this cannot be part of the portfolio used for open source hardware. But if you think about a processor like Risky or Cortex M4, if you think about APB or AXI bus or the UART SPI, I mean, who cares about the features of an SPI or a UART? The important thing is that it works. It is very well verified. It is very well documented with industry level kind of verification and so on. And the clear trend I see is that there are many companies pushing this open source hardware, for example, through organizations such as Open Hardware Group. I didn't talk a lot about this group, but Open Hardware Group is a consortium of companies. There are many industries in Europe and also US, all the world contributing to this. And they are putting together effort to develop a portfolio of IPs that can be used by anybody to develop system on chips, especially for, let's say, low power applications. For example, the processor I described before now is called CV32E40P, and it is the, let's say, Cortex M4 equivalent in terms of open source hardware. And there are also already a lot of IPs, all the AXI IPs. There is a 64-bit Linux booting processor, which is part of this group. And let's say this is pushed right now both by the industries through this group. There is another group which is called the Chip Alliance doing similar things, and also by the European community. There are a set of KDT calls where Europe is putting, let's say, money to try to develop open hardware IPs in order to build, let's say, this new ecosystem, which can be helpful for European companies. Yeah.
Maybe I would like to actually comment here. So I think I see two challenges to the open hardware myself when I was looking and talking to different companies. One is that we still have these big dinosaurs that are there. I mean, I'm not going to mention some of them, but you think about Synopsys, Mentor, and these guys, some of them, they get a lot of money with IP legacy that they actually have for doing Bluetooth controllers and SPI and stuff like that. Every single chip that you build that has one of these guys, they receive few cents, which actually considering the 75 billion devices is quite a lot of money. So I think these are a little bit the ones against the principles, and I have heard it that Synopsys is not very much receptive to some of these open hardware initiatives with some of the controllers, because yes, you build your processor, but you need to have an interface to the memory and external world. You still have to go through them to get the SPI interfaces and so on that are certified and so on. So I think with the open hardware part, what we need to get is to a point that I have been discussing with a number of them and with Davide Schiavone in the group as well and so on. We have to find the ways to get these new IPs, which are open hardware, also certified and really usable for these applications. Otherwise, we still will have the dinosaurs going behind us and not allowing it. But I'm fully a supporter of that. Now, the second part, which is I think for me a challenge there, is the software. So you think about all the software part that we have there. Traditionally, you have many of the big companies that are producing more and more the complete stack, vertical stack. You have Apple building the hardware, the software, the layers. You have Google, you have Huawei. All of them are trying to do kind of this type of thing. Especially now, since there is a competition between China and not China, then of course all the people in one side, they will build their own OS, their own system, and so on. So now we have to find a way. We had all these multiple kind of, you say, ARM Cortex M4 equivalent. What is the support for that? Because if you go to ARM, they have a whole bunch of domain of different applications, debuggers, and this type of things that makes the life very easy. And actually, I think this is one of the big challenges that we don't have in the open hardware yet. Because even now, when we build our own custom hardware, whenever you want to go, yes, to make a paper, to make a demo, looks nice. When you actually go to the company, and I can tell you a clear example, you go with Nespresso, you tell them, okay, I give you a RISC-V architecture. Okay, I can buy 20 billion. No, I can buy maybe 10. Yeah, but if I want to build my coffee machines, I have 20 million a year. How do I build them? And how do I support them and debug them and so on? It's a bit tricky to actually get into this because these people will not be there. But I'm fully supportive. I think we need to really work on that.
I completely agree. I think that, I mean, at the time being, RISC-V processors are being used in those applications where, let's say, the processor is hidden to the end user. So for all the applications where the end user need to program the processor and do its own application, I mean, the market at the time being is very low, but it is growing for a lot of applications where, the programming and the user interfaces are hidden to the final user. This is a real problem, and I think it will take, I mean, a lot of time, and it will be very challenging to reach that point.
I agree.
Yeah, there is one more question from the middle.
Do we actually have open hardware, or do we just have open RTL? Because if I want to design a system, I can get the RTL code for RISC-V or from open cores. But in order to actually make hardware, I'm still gate-capped by Cadence and Synopsys. Will we see a community project going in that direction, or will this always stay in the hands of two or three companies?
So I mean, there are also, I mean, open source RTL. Okay, of course, is just a very small portion of the whole open source hardware. But let's say, at least if you want to reach a real open source hardware, but at the moment, let's say, both from the technical and let's say legal viewpoint, this is at the time being the thing that is affordable. So I'm talking about technical and legal because yes, there are initiatives to do open source EDA tools. And the initiatives are both sponsored by European community and companies, but I see, let's say, the street to reach good quality EDA tools, open source EDA tools, very, very hard, even because, let's say, there are just a few companies that developing EDA tools, and also their EDA tools are not perfect, okay? They are still buggy and so on, and this it's a very big challenge. And on the other side, the other, let's say, very difficult street is the one towards open source silicon. And this is even more challenging because it's not due to technical, not only due to technical issues, but also due to, let's say, legal and confidentiality issues. So silicon manufacturers don't want to share with the community the secrets of their technologies, such as the distance between two metal one layers, because because these are confidential information, and this, let's say, is preventing the community to use these technologies. Also, in these cases, there are some initiatives that are allowing to tape out. There are few runs with the full open source stack in, I don't remember which old technology node, but it's a technology node since for old as old as 20 years. Do you remember? 180 nanometer. Yeah, there are some initiatives also for this.
Yeah, I don't think it will work.
Yeah, so I think what will work, I mean, from the perspective of what you say, open thing is that these are technologies that in the end, like what Davide said, they are very old. They don't have any real use or commercial use. These are the ones you can actually kind of think that they don't have a problem of releasing the actual specs for the PDK and the design tools. Now, having said that, as a commercial value, I don't think it really has a commercial value. But you think about really very low-cost sensors and things like that, fine, maybe you can build something, but I don't think they will ever make a commercial value. And with the huge, I mean, humongous amounts of money that they're investing on new factories and so on, this is not something that's going to be actually changed. So I think specs and hardware and so on, technology, I don't think so. I don't think we're going to get anywhere there. I know a few cases, and I'm not optimistic there, but I don't have very good confidence.
I am also pessimistic like David, basically, about the open hardware. But one thing I have seen in the US, basically, especially defense industry, and DARPA has a lot of interest on open hardware and to go build basically systems for defense industry. So that is one industry they want to have their own tool chain based on this open source, hardware and all these things. So there are a couple of initiatives I have seen also from the US government side on that. But commercial, I'm quite pessimistic that these big dinosaurs are already unless and until they step forward and they try to do something, I think it's quite hard. Yeah.
Yes, to make not to make Davide nervous. I'm not against open hardware. I meant open manufacturing, open synthesis flows and process. This is what I don't believe. I think open hardware, I'm fully for it, but I think you have to then go with the normal manufacturers for making your chips.
So we are approaching the end of the panel, so thank you all for just staying with us up until here. Myself, I do have one more question. So calculus has been around for, I don't know, 2 centuries, something like this. We still teach it, still useful. And instead, in the AI domain, it seems that we have a revolution every few years. So I'm old enough to remember what Petri nets are. But then there were perceptrons, and then LeNet came, and then AlexNet, and now we have transformers. Everything seems to be in a state of constant revolution. But still we have to teach these things. So what do you think we should teach to students to be something useful in the long run? So that, during their career, 20 years in the future, they can still have the basic principles, basically.
I can start or you can start, yeah. So this is a good question. Again, as an academic, I have to say, I think in the undergraduate education, I don't think there is any way I'm in favor of specializing the course. I really want to go to the fundamentals. There was a long discussion also at my university and course curriculum development, and people, of course, want to bring all new stuffs here and there. But I'm in favor of keeping the math, more math, and the basic signal processing course, and all other perceptron design or network design and all this thing. But there is a but. But this thing is, education abstraction is increasing. If you see that in earlier days, undergraduate 4-year college was enough, quite enough for many jobs and many things. And more we are getting specialized. Then master's degree became like normal thing in education world, that people after 4 years of college, they go to 2 years of education, and then PhD, a lot of PhDs we are producing, in fact, unfortunately or fortunately these days. So I think more and more specialized courses and will come. And the advantage is that even if you don't have a formal degree, due to online education, and these new techniques and new tools you want to take into your position, that you want to learn and become more reasonable and more time-oriented to learn new techniques, I think online education gives us a lot more flexibility these days. So with that, I think that in the undergraduate education, I don't think there will be any change, and I'm not in support of that. Yeah.
I wanted to mention that at EPFL we have been doing a lot of discussion and brainstorming on different changes. One of the main, I think the only one, if we have to say, agreement between all the sections, no matter where you are, is that undergraduate education and fundamentals have to be taught. So maths, physics, we are even thinking now, for those that actually are PD students, actually you are lucky, but otherwise you will have again chemistry and some others actually on the first year. So these are things that actually are going to go back to the fundamentals, because in the end, the more you see that this is so, the way you said at the beginning, so multidisciplinary, you see people talking from many things and so on. We heard a question about how do we work if we have so many different fields. Well, you need to be able to talk to these fields. If you have never heard the fundamentals, you cannot go back to the roots to talk to these fields. If you are only a machine learning guy, you cannot talk to all the other angles that are there. You don't know the fundamentals. So that's why for a bachelor, I don't believe there shouldn't be any change. I think even more going to the roots. I think we're discussing even to have not only one first year fully common, but even half of the second year as well. So something like that. And then at the master level and specialization, I fully agree. But then I fully agree that you need to specialize, because otherwise you don't get to the depth to be able to really do something. Now, the beauty, and I think I'm not advocating to people have 3 masters, that's not the idea. It's the idea that if you are able to really get the fundamentals, you can actually specialize very easily in many things later on. Now, one of the nice things that actually I think we still have at the PhD level is that we make people learn to think. And that's one of the things that we can actually achieve with a PhD, that no matter what you do, research or no research, you let people think out of the box. And that's the way to actually realize you have to learn something new. So I think this type of mindset that is actually done in the PhD, that's why I think we have so many PhDs these days, that I think we should maybe propagate them a little bit more at the master level and so on. Not giving, yes, data science, this is a very hot topic for the next 5 years, there will be something else, but the fundamentals, okay, how do I go out of the box and think of something else? I think that should be maybe something that we should emphasize. But I think specialization is needed only when you know the fundamentals.
Yeah, I completely agree with both. And I have to say that in Italy we never left the fundamentals. I think we are famous for this. We do a lot of mathematics and physics and so on. And on the other hand, I think let's say is very important to keep all the courses up to date. Because every year the world is changing with AI, different techniques, different algorithms, and I think it's important to update the courses every year in order to let the student understand that this is a world which is changing very rapidly, so that they will be able to continue studying also after the master, because the world won't finish after the end of the master.
So I haven't covered point 5, but I think that I asked enough questions on my side. So is there anything else that you would like to ask the panelists? Yes, please, Lara.
So we talked a bit about the pitfalls of traditional machine learning. Like Davide was saying, sometimes you have groups that train 10 different models on 10 different data sets, and they don't publish the models, they don't publish the data, and it's hard to evaluate which ones are explainable and which ones, are actually measuring what we want them to measure. How do we do this in the edge AI community? How do we keep from going into the pitfall of, everyone just makes their own hardware, software, co-design system, and how do we evaluate, are there any benchmarks or common data sets that we can use to evaluate, fairly compare the different systems?
So you can answer,
Yeah, so it's a very good question. Actually, we have seen it confronted many times on medical data. So I have two. One is plain simple, which is we should simply not accept papers that they don't provide actually the data sets. Simple. I think it's actually something that I have been trying to advocate in IEEE for many years. When I was council president, I have quite a few societies that were against that, but I think we managed quite a bit of progress on that. But I think, simple, if you don't have the data sets and you cannot verify the experiments, the thing is not valid. The second one is how you really make it really that big corporations that have huge tons of data make it public, which is another one. Because no matter what you do, even if you want to collect data, you're going to collect, well, 10, 20 patients. You manage to do, you get 50 patients. But they have tons of data. You think about pharma, the pharma have millions of pieces of data. Now, the problem there is really very much that they don't want to, and there's no way to change that. And then I think there we need the support from the governments to actually help us. But on the academic side, I think it's very simple. You just simply don't get the data, you don't accept the paper.
Yeah, I fully agree. I was the ICCPS general chair this year. We introduced this reproducibility. You have to submit the code. You have to submit the Python script, you have to submit the data, we have to reproduce. So you cannot force, unfortunately, so we had to basically compromise at the end. So we gave a star sign that if you submit it, you get an award for doing that. That will be part of your paper. So to encourage people to submit these things. And many other communities are doing that. And in fact, we need to do it in every conference. In fact, we need to talk to our CIDA and other community, IEEE and ACM venues about that. That how do we make sure that every paper comes with data and reproducibility, instructions about reproducibility.
Yeah, I mean, I think that one possible approach to deal with this, okay, they were talking about training and models and Python, but I think that the same approach can be used use the open source hardware, for example. If you use what we are doing, you can contribute to it, put it open source, and you can be able to, let's say, show to the community and let the community reproduce the results. So this is a possible approach.
Very good question.
But I definitely agree. I think we need to have the lobby from the government to help us get that with the companies. That's a bit of an issue. In Switzerland, by the way, is going on right now.
So I think that's...
I'm not very optimistic on that side. Yeah, but I can push for the papers, publications, and all these things. Yeah.
So we are almost half an hour over time. So I don't know if there are burning questions that you would like to ask to the panelists. Otherwise, please join me in congratulating them.